Good morning. So yesterday we finished sort of the first bigger section of this series, which is to discuss how we can study if some theory has a phase transition and what kind of a phase transition it is. And also we could determine properties of these phase transitions by making use of these effective field theory techniques, and then maybe at the end of the day some simulations. So now today is kind of a transitional stage, so to say, because then the last two lectures are then what we really want to get out of these phase transitions, somehow, so to say, the signatures, so gravitational waves, baryogenesis, magnetic fields. But to get there, we have to first understand how the phase transition really happens in real time. And so that's the issue of this nucleation and dynamics. So now this dynamics is a little bit complicated. What I'll do is I will, in the first 45 minutes, I will mostly be drawing like pictures or so to try to give an impression of what is going on. And then in the second 45 minutes, we do a couple of nice little computations which can be done by hand to see a bit more what's happening. Okay, so this process of how a phase transition happens, it has kind of, or we to get grips on it, somehow we try to view it as a kind of as a collection of different steps. And so the first step is then a nucleation of bubbles of the low temperature phase. And so what this means is that let's take some snapshot of the medium, and now we have to go to a temperature which is a little bit below Tc. So there is some, that's very important, this we can understand then in the second part of today's lecture. There is some supercooling that has to take place. Phase transitions, when they really take place in the real world, they don't happen exactly at the critical temperature. One goes a little bit below. And so then when we are a little bit below, then the high temperature phase is metastable, and the low temperature phase would be the stable one. And so now, every now and then you can then nucleate some bubbles of the low T phase. And now these bubbles can be very small, and if they are too small, then they collapse. And if they are large enough, then they can start growing. And this we can also understand in the second part of the lecture. And so then you somehow, basically you nucleate bubbles here and there, and the big ones start to grow. And then they grow, and eventually they will fill the universe, so to say. Okay, so now the first thing then to compute is how, what kind of sizes of bubbles do you get, and how often does it happen? What is the rate of nucleating bubbles? And so that's somehow the first challenge. Okay, so then once the bubbles some bubble is large enough such that it starts to grow, then it's the growth of the bigger bubbles, so to say. So now this is also kind of, you would think that, okay, you get this bubble and it starts to grow, but then one has to stop for a while and consider the following. So suppose I have here some growing bubble. So now if I look at the medium far away from the bubble, then on the average it's at rest. If there's no if we are in the rest frame of the medium, Of course, the individual particles can go in all the directions, but on the average, medium is at rest. But also, if you look at the inside of the bubble, medium should be at rest. Well, just because of symmetries. If you're in the middle, you cannot go anywhere. I mean, it has to be at rest. There's no, you cannot create space out of nothing. So now the problem is, if you then imagine that there is this front, then I mean, if some front hits you, then if it hits you, you start moving. Normally, I mean, a shock hits you, you start moving. Or sometimes there are fronts which also suck you, like some, I don't know, some tsunami maybe sucks you in the other direction. And so that's a problem. I mean, if you're at rest here, and then you put here a front growing at large speed, it just doesn't match. It's a very basic fact, geometric fact. So you always have to have two fronts somehow, which are growing. And so then the first front can set you in motion, and then the other one can suck you back to rest, or vice versa. Very simple, but very important fact. And now this leads to two possibilities. There are two fronts, then there are two possibilities. The first possibility is that the inner front is the phase transition. So I will plot it like this. Now I plot the flow velocity, and then I plot r over radial coordinate over time, where the time is now the time from the nucleation, so when this bubble started to grow. So this basically gives me the velocity of these fronts. And so in this first case, the inner front is the phase transition, and then it looks like that there's first something here, and this something is a shock. It's a shock, and then it sets things in motion. So shock kicks you in motion, and then the motion has some kind of a profile, and then comes the phase transition. I don't draw the phase transition with a different color. This is the phase transition. So the velocity of the phase transition is often denoted by VW, velocity of the wall, and the shock is like a sound wave, but extremely strong sound wave, because in some limit it's a discontinuity. So the velocity of the shock is sort of usually very close to the speed of sound or a bit above it. Okay, and this case is called a deflagration. And then the other possibility is that the outer boundary is the phase transition. So in this case, I first have the phase transition, wall velocity, and now this wall velocity is then larger than the speed of sound. It kind of replaces the shock, but then there has to be this second front, and in this case in the second case, somehow the second boundary is kind of a weak discontinuity. There's a funny wave, funny flow profile here, and this is called has a funny name, rarefaction front, or rarefaction, rarefaction. This whole profile is, and there's then some weak discontinuity here at a low velocity. Well, this case is called a detonation. So it also sounds kind of more violent. So now in this case, well, I mean, these are very different possibilities, and so that's then another challenge. Somehow, challenge is would be for a given model to decide whether which case we have, and which is then the wall velocity. And so these are very important questions for somehow practical applications then of, amongst others, of gravitational wave production. Well, these are kind of hard questions from the microscopic point of view. And so we will not be going into these, but there's really lots of work, for instance, on this determination of the wall velocity in simple extensions of the standard model. So it's an important topic. And then, after a while, all these things start colliding. Okay, so maybe one thing I should have said, maybe familiar to many of you, but just in case, speed of sound in a relativistic plasma is very, very high. It's almost the speed of light. Well, more precisely, it's about 1 over square root of 3. So these are really violent fronts. I mean, detonation expands then also almost at speed of light. So you can imagine when these fronts with speed of light collide. I mean, it's kind of a major mess that comes out. And so bubble collisions, then it's a very loud event, sound waves. One generates lots of sound waves. Well, shocks are already sound waves, but then also these things collide, it generates more sound waves. And then it's very complicated also because hydrodynamics is non-linear, highly non-linear, so people think that there may be some turbulence and so forth. So it's a very complicated system. And so, of course, nowadays, one really looks at it with then simulations. Then after the simulations, people sometimes try to model the results with some ansatz or some kind of semi-analytic attempts, but really it very much relies on the simulations, what comes out from here. Okay, so that's now the sort of the general pattern. And so what we want to look at today in a bit more detail is this first part, the nucleations. Okay, so for the nucleations, there is kind of an intuitive picture. Which is the following, that we have now computed, as a function of our phi bar, we have computed some effective potential. And if we then were at a temperature, say, somewhat below Tc, then the potential, and if we did have a first order transition like we had at the very end of the previous yesterday's lecture, then we would be in a situation like this, where this is the high temperature phase and this is the low temperature phase. So if we now come from the high temperature side, then at first this would be a deeper minimum, but then just when we are already below this, well, maybe I should draw another curve. Just before that, we were in a situation where we were still above TC, so we were really kind of stuck here for a long time, and then this happens, that the other minimum becomes deeper. So how do we go from, so somehow then one should imagine that all the particles are kind of here. How do we go from here to here? Well, first of all, this is a classic problem in quantum mechanics, so one can say that one can tunnel through a wall. But then also we are in a thermal system, so we can always borrow energy from some fluctuation from the other particles in the medium, and maybe this thermal fluctuation just gives us enough energy. There is some height of the barrier here, and if we I mean, if we find somewhere the energy of the height of the barrier, delta V effective, then there is a probability that we tunnel above it. So it looks like there are different ways of going to the correct minimum. Now, it's a good picture to have in mind, but at the end of the day, ultimately both are limits of a more general of a single mechanism. And I will try to illustrate how it can be that these two things are limits of a single mechanism. So how can we do it? Well, so how do we? So there's a way to do nucleation in this funny theoretical framework that we have introduced, this Euclidean or imaginary time field theory. And now, okay, you might say that we introduced the whole imaginary thing to do thermal physics, but the important thing is actually we can do the same also for the vacuum physics. And indeed, this nucleation in the Euclidean field theory, it also incorporates normal quantum mechanical tunneling. So how does it go? So we have this action, the Euclidean action of our field. So now what we can do is search for extrema. And extrema are solutions of the equations of motion. ds d phi is 0. So now it can happen that we find two types. As with usual functions, the first type is that this extremum looks stable, locally stable, so at least metastable. And mathematically, we say it like this: that we take kind of the second derivative. So now these are functional derivatives. So second derivative of this action is really a differential operator. So it's a differential operator. If you think of an action, it has d mu phi, d mu phi. If you take second derivative, it's kind of d squared, like a D'Alembert operator. So it's a differential operator. So this differential operator has only only positive eigenvalues. But then the other possibility is that we have like a saddle point. And a saddle point in the same sense as we saw at the end of the lecture yesterday, that there is at least one direction where the curvature is negative. The other directions it can be positive, but one direction curvature negative. So this fluctuation operator has, well, at least, but often exactly one negative eigenvalue. So what happens with the positive?
Why the case 1 is called metastable instead of stable?
Oh, because it can be, I mean, if it were here, if you look at the curvature here, it's also positive, but it's metastable. This would be the stable. Okay, so now the statement is, if we find the solution of type, if find solution of type type 2, and more precisely, not only a solution of type 2, but it has to have certain properties which so if find solution of type 2 which is, so it has to be non-trivial, so space dependent, so space-time dependent. And so I denote this solution now by that phi would be, then the solution would be, I denote it by phi hat, this would be solution. So it would be a function of tau and of the space coordinates, tau and x. Second, it has to satisfy certain boundary conditions, namely far away we are in the, and now the jargon, one often calls this this metastable state, one often calls this the false vacuum. It would be proper language at 0 temperature where we can really talk about the vacuum. In a thermal system it's not really a vacuum, but we can still call it, we still often refer it to as the false vacuum, which means that if I send x to infinity in my solution, then, okay, in this picture it would mean that the phi goes to 0, because now I've assumed that the normalization of the field is such that in the metastable state the field is 0. Okay, now furthermore, it has to be periodic in tau, because that's all our fields in this path integral, they are periodic. So this one also has to be periodic. Beta x phi hat 0 x. And it's a solution, so it satisfies the equation. Then we call this solution, we call it a bounds. That's another other jargon word. But now, I mean, maybe it's a bit formal, but the important thing really is that if you were, I mean, in this picture, we can find certainly solutions of the equations of motion, namely a field which is constant here, or we can find a solution which is constant here. These are the stable solutions. But the unstable solution is we exclude these constant ones. We have to have something which is a solution, but it's not constant. But far away, it's here, and then it does something in between, and it's a solution. Okay, so now what do we do then? Well, it can happen that we find many such solutions, and then the most likely one is the one with the smallest action, because remember in our path integral we have e to minus se. Most probable, let's call it an event, this nucleation is the one with smallest action. So action evaluated now with the solution. Now it's not quite simple to prove this, but I think intuitively it may be clear that the least action you get if you take the most symmetric solution. If the solution is not symmetric, then there are ripples, and ripples, that means derivatives are non-zero. And in this Euclidean action derivatives, everything comes with a positive sign, di phi, di phi. So if you have too many positive derivatives, it costs more. It gives something positive. If you manage to eliminate as many derivatives as possible, then you don't pay a price for that. This is, let's say, probably, but can be then proven under certain conditions, and this should be the most symmetric one. So let me now sketch what kind of solutions we might expect then. So we start now with 0 temperature. Because if this formalism is going to work, it should also work for the quantum mechanical tunneling. So now I kind of draw the space-time. And here I put the tau, and here I put the spatial directions. And now you remember that the periodicity was beta, so 1 over temperature. So if I send temperature to 0, then beta goes to infinity. So then the tau axis is infinite, like the spatial axes are. And so in this limit, the Euclidean spacetime is O4 symmetric. The spatial directions and the time direction are just the same. They're all Euclidean directions. And so therefore, the solution, whatever it is, it should be like a round object in this 4-dimensional Euclidean space. And this object we call, so this is 4D symmetry. So it's quantum tunneling. We say this is then quantum tunneling, depends on tau. It's 4D symmetry. And generally we call this object, has a famous name, it's called the Instanton. So just a reminder, why Instanton? Well, really it means that somehow the event is instant in real time. But in this mathematical imaginary time, it's not instant, it has a size. It has exactly the same size as in the spatial directions. So mathematically it's an extended object, but physically the nucleation should happen, so to say, instantaneously. Now, of course, instanton is one of our favorite words in quantum field theory. So it's used in many, a little bit different meanings as well. But so this is a generic meaning, that instanton is a solution of the Euclidean equations of motion of the system. Then more specifically, one talks about instantons, for instance, in Yang-Mills theories or in some supersymmetric Yang-Mills theories. Sometimes one even talks about the solution. In Yang-Mills theory, for instance, it's difficult. Well, it's not really in pure Yang-Mills. It's not even like we know exactly that there is this solution. It's more like we think that there might be something like that, or many solutions like that. It's only when you would take a Young-Mills and put some kind of a suitable Higgs field that you can explicitly construct a solution. So sometimes Instanton really means to some solution which you can explicitly construct in some Young-Mills theory. Here I mean a solution which one can explicitly construct in scalar field theory, and sometimes it's just a jargon for any kind of event, field configuration, maybe not even, strictly speaking, a solution of equations of motion, which somehow mediates quantum tunneling. So then the next case we do is we now we turn on a temperature. Well, what happens then is that our time direction is no longer exactly the same as the space directions, because then we have a finite beta, finite 1 over t. And now everything has to be periodic in this beta, because it's really a circle. But now one can imagine somehow, like with some good imagination, one can think that, okay, if we start somehow squeezing, then if we just squeeze a little bit, then probably the solution, well, is still there, but it gets squeezed a little bit, but somehow maintains a bit of its shape. So one then thinks that maybe there is a solution like this, that maybe in the middle it looks a bit like this, but then it has to be periodic somehow across the, so maybe something like that. And then it, well, so to say, then if you go to the second sheet, you would repeat the same shape. But yeah, some solution like that. Now it's clear when I break the symmetry, when I have 3 plus 1 d symmetry, well, it's less symmetry, so it's a more complicated looking solution. And this we say that it somehow has features of the quantum, because it depends still on the tau, but it also has features of the thermal, because it now feels the temperature. So this is sort of quantum plus thermal tunneling. Well, quantum tunneling plus thermal fluctuation. So let me just write quantum plus thermal. And this is sometimes called the caloron. So somehow using similar type of language, but now calorons standing for the thermal feature of this solution. Okay, so these are even, kind of even more difficult to construct in practice than the instantons, but still there's numerically one can construct such solutions in certain theories, and so we think that such things can exist. And then for us, maybe the most interesting thing is when we really go then to, so to say, very high temperature. Now, one can ask high compared with what? And later on Friday we see one example where we can say exactly high compared with what. But now for the moment I will just say somehow very high. Well, what does it mean? It means that we squeeze the temperature direction even more. Temperature becomes large, so then beta becomes small. And so now you can imagine that if you squeeze, then at some moment it starts to be kind of tedious to have this. Why would I want to have this curvature here in the tau? Because that also costs energy. So it's then better to just be straight in the tau. And this one calls now thermal tunneling, thermal fluctuation. It has only three-dimensional symmetry in the space directions. And now, why is this nice? Well, you see what we had in the action was the SE has an integral over 0 to beta d tau, then an integral over the volume d3x, and then some Lagrangian function of phi hat. But now, if the solution does not depend on tau, then I can carry out the integral over tau, just like we could carry it out when we were discussing dimensional reduction. In fact, this whole thing is kind of very much related to the dimensional reduction, exactly because the field doesn't depend on the time. So this becomes beta times integral over the Euclidean Lagrangian. And so now it looks exactly like e to minus SE is like a Boltzmann wave. It's exactly what I had in the beginning, namely e to minus SE is then sort of e to minus beta is 1 over temperature, and this value we could say this is then the energy cost, delta E, delta energy for instance, or delta free, actually delta free energy one should say. But it's a classical thermal fluctuation. But the important thing is now this, both the quantum and the classical, they come really continuously from the same formalism. So there's no, you don't need any clairvoyant to tell you when you should use the quantum and when you should use the thermal language. It all comes from the same. So in this case, we also have a nice name for these solutions. And it's a bit, the story is similar to the Instanton, that the name is used in a bit different meanings. But I would call these things generically, like those I would call instantons, then these I would call generically the sphalerons. It's like an instanton, but now in 3 dimensions. Well, then sphaleron has a more specific meaning to which we will come back on Friday. Okay, so now that's the basic picture. So now what I want to do next is to, I mean, maybe this sounds now a little bit formal. So what I want to do next is to show that actually this last case, where we already said that it should have a classical interpretation, we can really construct it in terms of classical thermodynamics. So bounds in classical thermodynamics. And now a small preparation for what we will then do after the break. Let's recall how the basic sort of thermodynamics is works for cosmology. Well, what I mean is from the textbook we know that, let's say, energy is Ts minus P times volume plus mu times n, and dE is dds minus P dV plus mu dn. And free energy is energy minus Ts, so it's minus PV plus mu n. And dF is then, okay, it's this Legendre transform, so TdS turns into minus S dt. Okay, so now one thing we do in cosmology is well, it depends maybe a bit on the era of cosmology, but anyway, what we do now, say electroweak phase transition or so, is there the chemical potentials are extremely small, of the order of 10 to minus 10 times the temperature. So we can neglect these terms. Anything which has a chemical potential, we just drop. And then the other thing we do is that the system is very large. It's the whole universe, so, or at least the horizon, within the horizon, but that's also large, has trillions of particles. So it's not useful to use these extensive quantities. So instead we consider energy density, so energy divided by volume, free energy density, free energy divided by volume, entropy density, entropy divided by volume. So let me now write what comes out from there, and since that we will then need in a moment. So okay, so first let's look at this. If we divide by the volume, then we get energy density is T times entropy density minus P. Free energy density, dropping these terms, is minus the pressure. And then what we then need is we need the D, the differential of the free energy density. So let's look at, let's write now big F is then the free energy density times the volume. That is minus entropy density times the volume times dt minus P times dg. And now if I take the differential here, I have two terms, df times the volume plus f times the d volume. But now I remember that the f is minus p. So this term cancels against that term. And then I can divide by the volume. And so I get df is minus s dt. Very simple. So entropy density is minus df dt. Okay. So I think with this we then can go on, and let's now take the break and continue in 15 minutes. Okay, so let's continue. So what we want to do now is, what I want to do is consider some jumps, some basic jumps. So for instance, the jump of the energy, delta E, I denote, well, that denotes energy just above Tc, Tc plus minus energy Tc minus. And so this is a very important jump. And so this jump is called the latent heat. Okay, so now let's take the delta E from here. So let me call this equation star, 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 star. So from star, it follows that delta E, well, then I can replace T by Tc because I'm exactly at the Tc. And then I have delta S. Then I have minus delta P. But now minus P is F. So if I use this star star, then the second term is plus delta F. And the first term is delta S is minus delta of the derivative of F. So now This comes from the third. So now you remember the basic properties of phase transition. So free energy is always continuous across the phase transition. So this delta F actually is 0. You go from one phase to the other, and the function, the basic thermodynamic function is continuous, but its derivatives can be discontinuous. And if the first derivative is discontinuous, we talk about the first order transition. And so this is the first derivative, and so this can be discontinuous. And so now, in fact, we can solve for that. Delta df dt is, well, it's trivial. Delta E we call L, so it's minus L over dc. Okay, so very simple computation. So what I want to do now is I want to Taylor expand delta F around dc. So delta F t is delta F dc plus d delta F dt t minus dc, and then the second order. But here now I know derivative of delta S is delta F is the same as delta of df dt, and this we know from there. And this is 0. This we already said is 0. So therefore this one is, to first order, it is minus L over dc d minus dc, which I can write more nicely as L 1 minus d over dc, omitting the second order terms. Okay, so that's how the free energy behaves when we go a bit above or below dc. It's the latent heat and then the first order difference. So why am I doing this? Well, let's do now the following. We consider a bubble of the low T phase. So I just take a bubble of radius r. And what I ask is what is the change? What is the change in the free energy that this bubble brings along with it? And since I'm now I'm assuming that I'm in the supercooled situation, then this low temperature phase is the preferred phase. Okay, so this delta F was defined to be the high temperature minus the low temperature, but the low temperature is the preferred. So this means that by going to the low temperature phase, I win. I have a lower free energy. I win. So I should take the low temperature minus the high temperature. So this means that I have to take that. That's the high minus low. Now I need low minus high. It's a minus sign. Is that with a minus sign? So that's the density. So it's minus L 1 minus d over dc, and then the volume 3/4 pi r cubed. Well, what this so far says, this is a positive quantity, and so it says, well, now it would make sense to have a bigger and bigger bubble, because then I win more and more free energy. But that's not the full story, because there's a boundary here, and boundaries always cost energy. There's a boundary term, and that boundary energy is called the surface tension, and so that's familiar from everyday physics, everyday experience. It goes with the area. So now I can plot delta F as a function of r. And so there is this negative term which wins certainly at large r, but at small r, this boundary term is more important because it's a lower power of r. So the function looks like this. It starts as starts upwards, and then ultimately the negative term wins. And so now, all of a sudden, the physics is very clear. We have here an extremum. That's now our extremum. And we call this the critical bubble. And if we have a bubble which is smaller than this, then the surface tension wins. And it collapses the bubble. But if we have a bubble which is larger than this, then it starts growing. And now it's a trivial exercise to find RC. We just take the delta F, take the first derivative with respect to R. So minus L 1 minus T over Tc 4 pi R squared plus sigma 8 pi R, and we set it to 0. And so I can put this on the other side. I can cancel 4 pi R, and so the solution is then, if I cancel 4 pi R, there's 1 R left here. So RC is then 4 pi R from here leaves 2 times sigma, and then divided by L 1 minus T over Tc. It's almost trivial computation, but now it's a very important result, because it says that if you go close to Tc, then it's more and more difficult to nucleate these bubbles because the radius diverges. And the reason the radius diverges is that if you go too close to Tc, then the gain you get from the free energies goes to 0. So you have to take a larger and larger bubble to compensate for the surface tension. Okay. And now let's still evaluate, well, roughly parametrically, what the delta F is at this extremum. Okay, so we have to put in the RC, and I'll just, all numerical factors I put here in C, they are trivial, but just to save a couple of minutes. And we see that here is R cubed, and R has sigma, so it would be sigma cubed, and then it would be L 1 minus T over Tc cubed, but there's one L in front, so actually it's L squared. 1 minus T over Tc squared. That's what you get if you look at this term. And if you look at the other term, you get exactly the same. Because R is, well, sigma squared. Now you multiply by sigma, so it's sigma cubed, and divided by L squared, 1 minus T over Tc squared. So this is and these two terms, well, if you do it carefully, they don't cancel. So you really are at the maximum, and you have this kind of an expression with some positive factor here. Well, it's positive because it has this up on the y-axis. And so again, if T goes to Tc, then this diverges, and it diverges pretty fast, strongly. And so if delta F diverges, then e to minus delta F over Tc, well, it goes to 0 very fast, so it's not doable. You cannot, the likelihood goes to 0 very, very fast. And so that's why you need supercooling. We need supercooling so that this factor is finite. And then the likelihood may be small, but in cosmology there's, in some sense, there's lots of time, maybe. And so ultimately, when the temperature goes down, then the probability becomes finite, and you can nucleate. Okay. Good. So now there's a nice exercise. I mean, in the first half of so in the previous 45-minute section, we we were discussing these fields and the bound solution with the fields. And now we are doing something completely different, just classical statistical physics. And so it seems like they are completely different descriptions, but they are not. And so exercise is the following. If we look now, we go to the limit that we have these Faileron type solutions. So high T, 3D symmetry. And also we go to the limit, as we did here, that we are to, so to say, very close to TC, so to leading order. Then and we take a theory which has just a scalar field. So S is now beta times integral over T3x, let's say 1/2 di phi plus some effective potential maybe of phi. Then the solution that we have to look at corresponds to the equation of motion one gets from here. And if I assume spherical symmetry, then it's really d squared phi hat dr squared plus 2 over r. I'm now using radial coordinates because I'm assuming spherical symmetry, and that should equal the derivative of phi. This is the Euler-Lagrange one gets from here assuming spherical symmetry. Euler-Lagrange. And now boundary conditions. Are that I say that the center of the bubble is at origin. This I can impose by saying that the derivative of the solution at 0 is 0. That kind of fixes the symmetry point to be at the origin. And then I say that far away I'm in the false vacuum. Here I'm in the true vacuum, but the derivative is 0. Far away I'm in the false vacuum. These were the constraints, and the periodicity is now trivial because we are independent of tau. And so now one can solve this in a certain approximation. Well, in this limit, one can solve it because in this limit, well, we kind of intuition already tells that bubbles become very large, and so one can make suitable approximations. One can solve it. And now the difference is that this was very nice, this classical thing, but the price we paid for the niceness and simplicity is that we introduced this parameter, the surface tension, somehow out of somewhere. It's kind of a phenomenological parameter, if you wish. But if you do it in a field theory where you assume that you know everything, then everything should also come out. So the latent heat would come out from the properties of the effective potential, but also the surface tension should come out. And indeed it does, and one can then show that the surface tension has an expression which looks like this, that we should integrate from 0 to the broken phase d phi bar of 2 times the effective potential phi bar minus the effective potential in the broken phase. So we get the same in this limit, but we know more. We know the parameters that enter, we know in terms of the parameters that appear in the action. So now often in practice people are then doing this kind of computations, and so that's why it's good, maybe a good exercise. Okay, so that much for the nucleation, and now I want to kind of, for the remaining 25 minutes, sort of change the perspective a little bit and discuss some kind of a conceptual, maybe a little bit conceptual issue, but which is very important and nice. Namely, I mean, now we somehow, you know, we were kind of building this whole picture from some bits and pieces, putting them together. But I mean, if we really think that we understand what's going on, we should be able to do it better. There should be somehow a unified framework where everything comes out from. And so, so what is the theoretical framework for incorporating everything? Well, this theoretical framework is really very important to statistical physics, very general, but somehow it's, unfortunately, one doesn't really normally learn it in statistical physics courses, or then somehow it comes at the very end and very briefly because time has run out. But it has actually sort of many names, a bit related. So one way to say it is that it's fluctuating hydrodynamics. It's also closely related to maybe a more familiar concept, which is fluctuation dissipation theorem. And there's a concrete implementation which I will show, which is the Langevin equation, which is a special case of all this. Okay, so this means we are what we are doing now is we are doing some kind of macroscopic phenomena. We are not discussing individual particles. We have really this medium, and it has some variables. And what we can say that we are doing, well, we are doing hydrodynamics. We say that the variables are the temperature, but now we allow the temperature to vary, say, in time and space. Then there is a flow velocity, which I denote by u mu. So there's a medium. One can always go, in principle, to the medium rest frame, but if one is in some other frame, then the medium flows. And then there can be an order parameter, like our field phi. So these are the usual variables of hydrodynamics, temperature and flow velocity. And then if we have a phase transition, we also have something which undergoes the phase transition. And so now the picture that we should have in mind is the following, that if we consider some quantity as a function of time, so for instance phi, and we start from somewhere, then usually this somewhere, if we throw it, let's say we throw a dice and we start from wherever the dice brings us, then it's not the correct, so to say, equilibrium state. It's somewhere else. But systems always tend to equilibrate, so it somehow goes towards something. But it's not a straight line because there are always fluctuations. And then at the end you'll reach the equilibrium state, but again it's not really constant, there are fluctuations. So sometimes, I mean, normally in statistical physics one does discuss fluctuations of quantities, but not really, very much in very much detail. So the first phase where one is going towards the equilibrium, this is kind of the equilibrium situation. But even in the equilibrium there are fluctuations. But the first phase going towards the equilibrium, we call it dissipation. Because dissipation means that in this case the field phi has kind of too much energy, so it dissipates the energy to the other degrees of freedom to the plasma, temperature and flow velocity. And then when you are in equilibrium, then there are fluctuations. Then it goes the opposite way, that the field has, so to say, found its home. It's in a nice place in equilibrium, but the medium doesn't let it to be there. It always gets kicked. Now the energy goes from the medium to the field. And that's why there are fluctuations. And so this fluctuation dissipation theorem says that these two things are kind of related. So now let's quite concretely see what this would mean for the scalar field. So equation of motion okay, maybe I'll start a new. So equation of motion for phi. Okay, so if we were in vacuum, we would write d mu phi plus v, maybe v effective prime. Phi is 0. But now, in this medium, we have to correct it by two things, namely these two phenomena that we have here. So first of all, this field, it just cannot evolve as it would evolve in vacuum. It loses energy to the medium if it's in the wrong place, and that's the dissipation. And now I put here a coefficient which we like to call epsilon, and then it has to be somehow covariant, so u mu d mu phi. So why is this dissipation? It's because if you think that you go to the medium rest frame, then the u mu has only the time component, and it's 1. And so then this is phi dot is like a friction. So this is friction. It's friction. Phi loses energy to medium. And now why is this important? Well, this, for instance, is what I mentioned in the first part, that an important quantity in this system would be this wall velocity. But the reason that there is a finite wall velocity is precisely because this field it has a profile, it's expanding, but it loses, there is friction, it interacts with the medium, and the medium stops its growth at a certain velocity. And so ultimately, if you knew this epsilon, you could solve the equation of motion, and this would fix the wall velocity. Okay, now maybe somebody who has worked on this knows that in general I should say that this epsilon is it could also be a function of the phi, like the effective potential is a function of the phi. So now I'm writing it as a constant, and in a certain limit, when the phi is small compared with something, you can take it to be a constant. More generally, it could be a function. Okay, so that's one part, but then the other part is that there are these fluctuations. So also the right-hand side is not 0. There are these kicks here. And so these are random kicks. This means that their expression value is 0, but then there is some 2-point function there, parameterized by some omega delta x minus y. And so this goes in the opposite direction. Energy from not from phi, but energy to phi from medium. And why is this important? Well, this is important, for instance, because it is this kind of the kicks that nucleate these bubbles. I mean, these bubbles are just fluctuations. because if you take random fluctuations, it takes a long while to get a big bubble nucleated. But that's exactly in the properties of these guys. There is a certain likelihood, in the end given by the Boltzmann weight, that you do get enough sort of simultaneous kicks in a certain direction that you then get a supercritical bubble. You nucleate energy, and this leads to the nucleations. Okay, so now and so in principle we should be solving this. Well, we should be solving this together with then some hydrodynamic equations because the UMI is also a variable. But this is the phi part. So now you may, I'm just stating this somehow, and you may wonder if there's anything that can be done to consolidate this. And now there's a very nice little computation that we can do to understand a bit under which conditions this is the case and so forth. So consider medium rest frame. So only the zero component of flow velocity is non-zero, and a free field. M squared phi. Okay, so now if I do that, then the equation looks like this. I have the D'Alembert operator, then I have plus epsilon dt, and okay, maybe I'll even write this explicitly. So I have dt squared, then I have minus nabla squared, and then I have plus m squared. Phi is chi. So this is now a textbook example of a differential equation. In electrodynamics, for instance, this is what we have all the time. We have Maxwell equations. So left-hand side, some second-order differential operator operates on the gauge potentials. Right-hand side is some currents and densities. How do we solve that? We solve it by introducing a Green's function. So let me call this operator. Okay. Let me call this operator O. So the solution is that phi x is integral over y Green's function, which brings the information from the source at y to x. And the Green's function then satisfies the condition that if the operator O acts on the Green's function, we should get the delta function. Because you see, if I now operate on the x, then I get the delta function, then I can integrate over y, and then I get chi at x, and that's what I had here, it's chi at x. So that would work. So now, actually for this case, it's simple to write the Green's function. Write down the Green's function. Namely, I claim that this Green's function is well, it's easy to write the Green's function in a Fourier representation. So I claim that it is e to minus I omega t plus I k dot x divided by minus omega squared minus I omega epsilon plus k squared plus m squared, which is our ek squared. Well, how is that? Well, proof is simply if I operate now with the O on the GR, then okay, dt gives exactly minus omega squared. Epsilon times dt drops down to minus I omega, so it gives this term. And then minus nabla squared gives plus k squared and m squared, so it gives exactly this term. So if I operate, then the terms upstairs, they cancel the terms downstairs. And so then I'm left over with the integral over the phase factor, and this is delta x. So that's how it works. Okay, so now what we do is then the following. Now we know the solution. So now in cosmology very often what we really want, we consider, well, often we consider 2-point functions. These are kind of well, cosmic microwave background, we consider 2-point functions. Propagators are 2-point functions. So 2-point functions very, very frequent. So consider now the 2-point function of the solution. So now how I would write it then is I use twice this representation. Maybe I, instead of y, well, I used y here already, so I call the variable maybe z. Once I call it z, so gr x minus z, psi z, and then I call it w, gr y minus w, psi w, and then I take the expectation value. And now the expectation value, it's a thermal expectation value, but the thermal expectation value is the expectation value with respect to the noise. That noise, these fluctuations, that is the thermal motion. So that is the expectation value. But this we know. This is our omega times delta z minus w. So actually, we can carry out one of the integrals, for instance, the integral over w. Then we are left with integral over z. Y minus z. Okay, so now what I do then is I insert, I know the Green's function, it's here. So I insert the Green's function in the Fourier representation, and there are two of them, so I insert it twice. And then I put the z integral inside. So there is minus I, like with k dot, let's say this one, x minus z, and then there is minus I q, this one, y minus z, and then there are the denominators, so minus. Okay, let me save space. I write the denominators being this one. I keep them implicit for the moment, because now what I can do is I then integrate over z, and if I integrate over z is here and z is here. So this gives me omega k q denominator. Well, let's say denominator with k, denominator with q. I get denominator with k, with q, but the integral over z here gives me, this comes with the same sign, so it gives me delta k plus q. And then I'm still left with minus I k dot x minus I q dot y. So, and so in total I get integral, now I can integrate over q. Left over is integral over k e to minus, q gets replaced by minus k. So I have minus I k dot x minus y, denominator with k, denominator with minus k. Okay, so it was a bit, some steps, but now we have a very simple expression, and we can go a couple of steps further, and then we are done, because what I do now is what I do now is I then specialize to an equal time correlation function. Also, it's very physical, equal time. I mean, when we measure the CMB, it's kind of equal time. Well, you could discuss that, but I mean, roughly speaking, it's equal time that the photons were emitted. So let me put now times equal. Well, when times are equal, then that part cancels from here. And so then I'm left with the spatial integral and then no omega here because the times are equal, but I still have the omega integral, the integral over the zero component of k. And now I write this, and this is minus infinity to plus infinity. And now let me write this. It's kind of a nice integral, so let me now write it explicitly. So minus omega squared minus I omega epsilon plus ek squared. And then in the second case, it's with a minus k. But most of the terms are quadratic, so nothing changes. But the middle term with the friction is not quadratic, so that changes. It's plus I omega epsilon plus ek squared. Okay, so now this is a very nice integral to do. I mean, with the residue, well, there are 2 poles here, 2 poles here. 2 poles are in the lower half plane, 2 poles in the upper half plane. You choose whichever way you want, and you pick up the both poles and do the integral. And lo and behold, the answer is extremely simple, namely okay, let me still draw here omega, so there are some poles. Let's pick up the poles in the upper half plane, go around, and what comes out is the following: is 1 over 2 epsilon ek squared. Sort of, when you take the first few steps, it may look a lot more scary, but if you do everything carefully, then almost everything cancels and you get this very nice expression. So now this should look familiar, because in the first lecture, we were already discussing propagator of a scalar field. Well, and then there was this more complicated propagator, but then we were discussing the propagator, scalar field propagator in the very infrared for small energies. That was the whole infrared problem issue that we were discussing. So in fact, this has exactly the form of the, well, omega n equals 0 contribution to the scalar propagator, or put in other ways from yesterday, of the dimensionally reduced dr, because that was for the 0 mode case of the dr propagator. Well, it has a form. Now it has the form. It should not only have the form, it should be the same. I mean, we know, yesterday we did all we could, and we were really convinced that this is the right way to do things, to compute equal time properties. So certainly that must be the correct answer. So it must be the correct answer. And however, there we had the propagator was T. I mean, was T over EK squared. There was the temperature upstairs. But now we have two parameters, so no problem. So actually we are now done. So there are two important issues, so conclusions from here, summary. Summary point one is that these two coefficients in the Langevin equation, the dissipation and the omega, which describes fluctuations, they are not independent, they are related. And that is exactly the fluctuation dissipation theorem, which says that they are related. And now we can read off the relation. The relation says that omega divided by 2 times epsilon is T, must be T. So omega is 2 times epsilon times T. So this is the fluctuation dissipation relation. So that's an important issue in statistical physics. And then the second thing which is important for us is that now somehow the whole thing, it kind of, I hope it gives now credibility to this Langevin equation. So we see that the Langevin is not a completely different description of what we were doing. It's a generalization of what we were doing. With the dimensionally reduced theory, we were looking at equal time correlation function. Now we checked what comes out from the equal time correlation function to get the same. But with the Langevin, we could also look at non-equal time correlation functions. We could look at time-dependent phenomena like these nucleations. And so this Langevin, or more generally this fluctuating hydrodynamics, it generalizes dr to time-dependent phenomena. And now I should still be a bit careful, so not to all time-dependent phenomena. It's still an effective description in the same sense as the dimensional reduced theory. It was an effective theory. We had thrown out some higher dimensional operators. This is also, more precisely, it is correct for, so to say, low energy, slow time-dependent phenomena. But this is exactly what we want, for instance, in these nucleations. They are very rare events. And if we are able to describe how the plasma behaves at long time scales, slow events, slowly happening events, then that's what we need. And so that's why this framework is so useful and should be somehow in the toolbox. Okay, I think that's all for today. And so tomorrow then we go from here and discuss then gravitational wave production. And again, it's a topic which to do everything is too much when we did simulations and stuff, but we can again do some snapshots from here and there. And part of them are actually a little bit related to what we already did here. So, okay, good.